Well, we're going from the actual A-level part of waves, so basically that excludes progressive waves, blah blah blah. It goes on polarization, stationary waves 2, and we'll see how far we get after that. So polarized light only vibrates in one plane. So I'll explain this animated first. This was from a computing video. So basically, say you had one thing, then you had another thing, then you had another thing. Yeah, these are three polarized light plane things. So this one has this, sure. And this one has this. So basically what it does is this one, the first square, will let all kind of waves through. Blah blah blah. Just like that, all kinds of waves through. Now when it gets to this one right here, it will only let waves that follow this pattern through. So that is only one type of wave. And then when it gets to here, as this wave follows this pattern, it won't be able to get through here. Thus it stops. Lovely. So now we get into this. So polarization direction. So just imagine this. Imagine you hold a rope and shake it so it forms a transverse wave. Transverse wave is obviously the up down one. If you shake the rope from left to right horizontally, you will form waves that are horizontally plane polarized. This is because the waves lie on a horizontal plane. Polarization direction 2. If you shake the rope up and down, you will form a wave that are vertically plane polarized. This is because the waves lie on a vertical plane. These are the two polarization directions, horizontally or vertically. You can have a whole range of these up to the angle 0 to 360, and that would be like, you have to do that in radians, so divided by 180 over pi times by 180 over pi. So the evidence for transverse nature of waves. Longitudinal waves can't be polarized, this is because they're always straight, while transverse waves can be polarized. So how many planes does polarizing light move? 1. Wow. Oh, polarized light, yeah. If we shake a rope up and down, in what direction would the wave through the rope be polarized? Vertically, because as the rope looks like this, it would only go through vertical planes. Application of polarization. Polarizers only allow transverse waves at particular angles to pass through. This is useful for sunglasses and television transmissions and reception. So polarizers only allow transverse waves at particular angles to pass through. Polarizing materials. An example of a polarizer is Polaroid material. This is used in sunglasses. Sunlight is unpolarized, so basically the lenses on your sunglasses are the things that stop the bad waves from getting in. And you can say the same for these kinds of things, but is basically all the same thing. So reflection as polarization. When unpolarized light reflects off a transparent surface, the light becomes polarized. So the polarization in partial and parallel to the surface. And this is what I explained at the start. And aerials. So basically, if you've seen your TV aerial, obviously it looks like either it looks like this, or it looks like that. So this one only lets in horizontal waves, while this one only lets in vertical waves. Simple. If a radio transmitter sends out vertically polarized transverse wave, the spokes on it. If a radio transmitter sends out vertically polarized, but theoretically it was the same difference. Polarized only allows short wavelength waves at particular angles to pass through. Is it short wavelengths? Pretty sure it's just transverse waves, yeah. Longitudinal can't, like you physically can't. Okay, if two identical polarizers are placed at right angles to one another, what would happen? No light will pass through. It just wouldn't work. Because it would go through one way, then it would just stop at the next one, and it's like, what's the point? So stationary waves, let's get it. So stationary waves are important physical concepts. They can be created when a wave interferes with its reflection. So a stationary wave is formed when two progressive waves, each with the same frequency and wavelength, move in opposite directions and interfere. So obviously here this one's going this way, then this one's going that way, so these two interfere with each other. So nodes. Nodes are a point of stationary waves at zero amplitude, so this part is a node. And antinodes. Antinodes are placed on stationary waves at maximum amplitude, so obviously the trough and the crest. Simple. So node, stationary point, zero amplitude. Antinodes, oscillating point, maximum amplitude. So obviously these are simple. Okay, resonance, the first harmonic. Stationary waves can only have a resonant frequencies. The resonant frequency happens when the distance between the two fixed ends is an integer multiple or a half length, half distance. The first resonant frequency is the first harmonic, so that is like the lowest frequency possible. The second harmonic is the double frequency of the first harmonic, so it is just bigger. The frequency is twice as big. And third harmonic is 3 times as big as the first harmonic. Simple maths. The second resonant frequency is twice as resonant frequency and has 3 nodes. I thought I meant something else. Standing waves can only occur at certain frequencies. Right, we check the thing for this. Standing waves can only occur. Stationary waves can only occur at certain frequencies. At resonant frequencies. Ingenious. Parts of stationary waves. Points of stationary waves at zero amplitude. Node. Antinode, because it has to be. Antinode. Simple. So when do resonant frequencies occur? So this occurs is equal to that one. Yeah. So what is the point of stationary chord that has zero amplitude? It is the node. The node has zero amplitude. Good jobs. I put on do not disturb mode. The hell is this? It's garbage. Okay then. I cannot be bothered. I will throw something at you. So this practical investigates how the frequency. We don't need a frequency practical, do we? Okay, we move. No, we don't, because you need the theory.